All right, this is the CS 159 Fall 2021 Midterm 2. So let's go ahead and get started. All right, so our first question. So here we're going to answer the first two questions as they relate to all three of these variables. So as we see here, we have a piece of code. So we'll go ahead and get started. So we got X, Y, and Z that we need to keep track of throughout the code segment here. So initial values of each of these is 3, 0, and 3 respectively. So the next thing that we jump into here is this first if statement here. So as you notice, there's no parentheses around any of the ands or ors. And so what I usually like to do is add them myself. So as if you remember, or you can look at the operator precedent table, and comes before or. So basically we'll need a set of parentheses here and then a set of parentheses over here to better visualize kind of what's going on. So let's take a look at this first and statement. So we're doing plus plus x. So we're going to increase x before we do it. So now x is 4. And so 4 is true. So then we do go to the second part of this and we do y plus plus. So we don't increment the y till after. So this becomes a 0 right here, which means this and is 0 or false. So since that's false and it's an or, that means we need to go to the next part of it. And we also need to remember to increment y since we finished that and statement. And then here we have z minus minus equals 2. So the minus minus means it happens after. And we see, does 3 equal 2? It does not. So this means that this is also false, which means the whole statement is false. But we do decrement the z to 2 here. So then we go on to our next else if statement here, since the if statement was incorrect. So we do plus plus x. Well, actually, first, before that, we should remember our operator precedence, and we do and before or. So it's going to be a separate set of parentheses over here. But we do need to do the first part of this or statement first. So we'll do plus plus x, which means we do it before. So we have 5. And then we take the not of that. So the not of 5 is just going to be false. It'll be 0. So this is 0, which means that we do the second part of the or statement now. And so the first part of the and is a minus minus y. And if you look, y is 1, so we'll decrement it to 0. And so we have 0, but then we take the not of it. And the not of 0 is, of course, 1. So that is true. So then we need to go to the second part of the statement here, which is minus minus z. So minus minus z means that it'll be 1 now. So we're doing 1 and 1, which is 1. So that means this whole else if statement becomes true. So that means we end up going down into this else if statement, into this statement here. And this statement's kind of weird. I've never really seen much like this before. You probably will never want to write code like this. But effectively, what it's doing is it's just doing z equals x, which is a value of 5, is greater than or equal to 0, which is the value of y, and then that's greater than or equal to z, which is 1. So basically, if we were to draw parentheses around the whole thing, it would look like that. So if we go through this through order of operations, 5 is greater than or equal to 0, that's true. So that becomes a 1, and we say greater than or equal to 1, which is also true. So that becomes a 1. So then we're setting this equal to z. So that means z is now 1, but z was 1 before, so we're not really changing much. And then once we finish that, this else if statement here, we don't do that, and we also don't do the else since we already went through the else if branch above. So we have our final values of x, y, and z here. So this means that our answer for this question is going to be 5, because that's x is 5. And then if we move to the next question here, it asks, what is output generated by the program for question 2? Well, we just did this in the previous problem, and it's asking about y and z. So if we look here, our y value is 0, and our z value is 1. So that means the correct answer for 2 is A. And if you're just now coming with us on question 2 here, just go back and watch the previous info for question 1 to see how we got that. All right, moving on. Okay, so question 3. Which of the following logical operators short-circuited in the program? So this is the same exact code piece that we were looking through. And if you remember, we pretty much, every single one of these here, these operators here, we never short-circuit on any of those if and else if statements. You may be thinking, oh, but we short-circuited here because we never did that. But that's not actually a short-circuit because we never actually ran it. The short-circuit more occurs like if we have this x plus plus x, and we run it, but then we don't run the rest of it in the same conditional branch. It doesn't mean that we didn't run them all together down here. So that means that this answer is none of the above because we didn't short circuit on any of the questions. All right, number 4. What is the output generated by line 26 in the program? And line 26, since I don't have any number lines here, is the line down here, this final print statement. So this looks like it's an array problem. So we're going to go ahead and jump in. And so the first thing that we notice is we have two arrays. We have the grade array and the credit array. So the first thing I usually like to check is the size of our arrays. So num classes is 6, so I usually count. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So both of those are completely full. Otherwise, they get filled with zeros on the end of them. And so now we can jump down into our for loop here and kind of take a peek at what it's doing. So I'm going to create two things to keep track of the points and the credits variables, as those are going to be what we're updating. And so one thing we can do too is this num classes minus 1 here. So we're going to start at I equals 5, which is the last index in the array. So both points and credits start out with a value of 0. So then we do credits plus equals credit at I. So if you remember, currently our value of I is 5. So we're going to do credits, and we're going to do plus equals credit at I, which is 5. Or credit I is 5, sorry. And so credit at 5 is 0 right there. So that means it's just going to be 0 still. And then we have this switch statement, which switches upon the condition grade I. So currently we are at I equals 5, so that's this element here. And so all of the cases for this are their characters. If you notice, we have A, B, C, and D. But all these values up here are decimals, or integers rather. And so we need to make sure we look at our ASCII chart and convert these to characters so that we can kind of refer back to it. So 65, if you look at the ASCII chart, is an A. 65, A. 67 is a capital C. 66 is a capital B. Another B here. And then 80 is not an A, B, C, or D. So I'll just write unknown here because that's the unknown case. So we're starting with 5. So we switch at 80 here. So that means none of these cases are going to be fulfilled. So we just go straight to the default case. So we print out unknown grade, but we don't increment points at all. So then our I value, we loop back through to the start, and our I value now becomes 4. So we do credits plus equals credit at 4. So credit at 4, the fourth index here is this 66 here, but we're looking at the credits array, which is 3. So we add 3 to our credits. So that becomes a 3 now. And then we go into our switch, and we switch at grade I. So grade at 4, we said that was a B. So we come right here. So then we do points plus equals credit at I. So our credit at I, as we said, was 3. So we do 3. And then you might think, oh, and then we're done. But they didn't include any break statements in any of our cases. So this actually falls through to all of these case statements here. So we actually end up adding credit at I 3 times. So we do credit at I plus credit I plus credit I to get 9. So 9 is now our current points value. And then we actually print unknown grade again at the end. So then we loop back through. I becomes 3. So credit at 3 is 2. So then we add 2 to this, becomes 5. And then grade at 3 is 66 again. And since our credit was 2, we just add 2 3 times again. So 2 plus 2 plus 2, which then that's 6. Then we add it plus that 9 becomes 15. And then our I decreases to 2. And then we'll have to remember we stop at I is greater than 0. So we'll keep that in mind for later on. So then I at 2, our points value is 4. So our credits increments by 4 up to 9. And then we look at credit at 2, or grade at 2 rather, and we see that's a C, right? So that's this case right here. And in this case, we only do it twice. So we do increment points right there and increment points right here. So we just add 4 twice. So we do 4 plus 4, which is 8, plus 15 is 23. And then we loop back through the for loop again. Now we're at 1. Credit at 1 is just 1, so we increment by 1 to get 10 here. And then on our switch, we switch upon A. So this time we have one here, 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 and here. So we increment it 4 times by a value of 1. So 1 plus 1 plus 1 plus 1, which is 4, of course, which increments up to 27. Then we decrement our I again, and we remember to check our loop condition. I is greater than 0. 0 is not greater than 0, so this breaks out finally. And then it has us print out our GPA, which is just points divided by credits. So 27 divided by 10, and we print out 2 decimal places with that. So that is 2.70, which is C. Okay, number 5. So just like we were talking about in the previous question, in question number 4, you might want to take a look back at that if you're unfamiliar or if maybe you got the wrong answer for it. But if you remember, none of these case statements down here, none of them have breaks. So that means that the default case is going to hit on every single loop. And if you remember, we're looping from 5 down to I greater than 0. So we're going to do 5, 4, 3, 2, 1, and then it stops. So that, of course, is 5 loops. So that means that the unknown grade is going to be printed 5 times. All right, number 6 here. So it's saying we are looking at the same piece of code, but now we change the expression on line 12, and line 12 is this for loop right here. We change this condition right here to I is greater than or equal to 0 instead of I is greater than 0. So all this does is this means we loop one last time, because before we never touched these I, or the index of zeros here, so we never touch those. And so if we use our code from the previous question, we'll remember that our points and credit after the 5th loop was 27 and 10. So then we can just basically do the loop one last time. So if you remember, 65 is an A, and so credit at 0 here, credit 0 is 3, so this will increment up to 13. And then we switch at A, which is this condition here, but this is going to filter through to all these case statements. So we're going to add it 4 times. So we're going to add 3 4 times here to 27. So 3 plus 3 plus 3 plus 3 is 12. Add it to 27, we get 39. And then our for loop ends. So then at the bottom here, when we do 39 divided by 13, that gives us 3. We're still putting 2 decimals, so that's 3.00, which is the correct answer. All right, our first true false, number 7 here. Which of the following statements regarding the usage of the switch construct is false? Okay, so let's just go through each one of these. So no 2 switch case labels can represent the same constant expression value. And so this is actually true. So basically what it's saying is we can't, if we have like a switch here, right, we can't have case 2, do some code, case 2 again. We can't do that. That's not allowed. You can only have one constant expression value. It can only be represented once in each switch statement. So that's what that question is stating. So that is false, or that's true. So this is not the correct answer. B is unintended association of 2 switch case labels with a common set of actions is a logical error. So this is true actually, because no compiler or runtime errors are going to occur if you have a common set of action that's unintended, because this is basically just a logical error that you just accidentally made the logic of the 2 the same, but the compiler is never going to throw any warnings or anything because you're not like doing anything illegal in the eyes of the C language. So that's true, so it's not a correct answer. And then C, each switch case label is the keyword case followed by a constant expression. And as we see up there, or as before, that is true because we'll just have case and then 2. I just realized when I wrote that switch, I did the cases a little bit wrong. I put the colon in the wrong spot, but the idea is still the same. But basically, yeah, that's right. So this is case, and then this has to be some constant expression here. That's followed by the by the keyword case. It can't be something that's variable. It has to evaluate to something that's constant. So this is true, which leaves us with a lovely none of the above answer for question 7. Okay, what is the output generated by the program for question 8 here? So it looks like we have a little loop here with a pretty big number, which usually means that it's probably going to be divided down to 0 or something of the like. So let's keep track of our 2 variables, x and y. So x starts out at 1, 4, 2, 1, 9, 1, 0. It's a pretty big number, and y is 0. So this loop continues while x is greater than 0. X, of course, starts much larger than 0. So let's take a look at that first expression. It's kind of a weird one, the two equals, or the 2 exclamation points rather. And so if we do the x mod 10 first, and so x mod 10 in this case is just going to be 0, right? And so then we take the first exclamation, so we knot it, so that becomes 1. And then we take the next exclamation, so we knot it again, so it just becomes 0 again. And so we just add a value of 0 to y. So nothing exciting happened on that first one. And then this next part is we do x equals x divided by 10 minus 1. And so we have to remember this is integer division, so there's no remainders or anything. So when we divide that big number by 10, we basically get rid of that 0, and then we subtract by 1. So then we get 1, 4, 2, 1, 9, subtract it by 1 to get a 0 instead of that 1 there. So that becomes our new number. So if we kind of take a more high-level overview of what this loop is doing, this will help speed up the process a little bit. Is this x mod 10, and then we do two knots. That basically just says if the number is a 0, just keep it as a 0, like we saw before. Or so basically the x mod 10 gets the rightmost digit, and then we say if the number is a 0, keep it a 0. But then the two knots, what it'll do, so say x mod 10 becomes 8. So then we take the first knot, so it becomes 0, then knot it again, so it becomes 1. So basically, if the number is not a 0, then it becomes a 1. Otherwise, it's a 0. So we can use this to our advantage to kind of speed it up. So on this next iteration here, when we mod it, it's just going to be another 0 again. So we're just going to be adding a value of 0 yet again. Then we divide by 10 and subtract by 1. So we get 1, 4, 2, 1, 8 this time. And then on the next iteration for y, that digit x mod 10 is 8. So as we discussed before, the 8 becomes a 1. So we add a value of 1 to y. And then we divide it by 10 and subtract 1 to get 1, 4, 2, 0. And so x mod 10 becomes 0. Take the double knot, that becomes 0 again. So we just add 0 to y. So it stays as a value of 1. Then we divide by 10, subtract by 1. We get 1, 4, 1. And then we mod by 10, we get 1. Take the double knot, it just still stays 1. So then we add a value of 1 to y to become 2. Divide by 10, subtract by 1, we get 13. And then we do x mod 10, 13 mod 10 is 3. And then double knot is just mean the 3 is going to become a 1. So then we add 1 to y. And then we divide by 10, subtract by 1 yet again to get a value of 0. But this time, remember, x has to be greater than 0. 0 is not greater than 0. So the loop finishes. So we have a final value of y is 3 for question 8. So kind of a weird one. Alrighty. Question 9 here. So this one asks, how many times is the loop control expression evaluated in the program? So you might be inclined, and even I thought that the correct answer was 6 times. The first time you go around, you might think, why is it not 6? Because if we look back at the previous question, if we count this up, we did 1, 2, 3, 4, 5, 6 loops through it, right? Because this last one here, we didn't actually loop through the body because it finished. So we would think, oh, we only looped through 6 times. But it's actually 7 times, because if we look here, it says the loop control expression. What the loop control expression is this statement here. So it's asking how many times does that get evaluated? And so an evaluation of that is when we compare it. So anytime we have a loop, if we loop through it 6 times, the loop control is always going to be 1 more. So we actually compare 7 times because the 0 counts as an evaluation of it, because we see is 0 greater than 0? It's not, so then we cancel out. So that very last one becomes part of an evaluation of the loop control expression, which means that we look through it 7 times. All right, so question 10 is relating to the same code that we were looking at before. So it says that the variable x is now initialized to this new number. What is the output generated by it? So if we look here, we have 1, 4, 2, 9, 1, 9. So going back to question 8, we kind of discussed on what this while loop is doing. And so even at a more higher sense, if you see, so we said that if the digit is something that's not a 0, then we add 1 to y, otherwise we just add 0. So we also see that this x divided by 10 minus 1, basically what that does is it takes off the very last digit, but then it also subtracts 1 to the digit. So basically what this loop is doing is it goes through all of them and it sees how many numbers are there that are 2 or greater. Because if it's a 1, like this one here, it'll be subtracted to a 0, and then we just add 0 to y. So if we count it up in this loop, or in this number here, we have 1, 2, 3, we have 4 numbers that are 2 or larger. So that means y eventually is going to have a value of 4 for the correct answer. So if you go back to question 8, the same thing rings true here. So if we count how many numbers are 2 or greater in this one, we have 1, 2, 3 numbers, and y was 3 in that case. So it's helpful often for these questions to kind of get an idea of what the code is doing instead of just tracing it through, because sometimes just tracing it through is going to take a lot longer. So this can save you a lot of time. Alrighty, question 11. What is output generated by this new program that we have? Okay, so if you see here, we have another one of these looping type of questions. So we'll keep track of some of the variables. Let's leave some more room for ourselves. Cur and next. So initially, x is this pretty large number. Y is just 0. And cur and next are not initialized initially. And so we go into a do-while loop. So a do-while loop means that we're going to do it on the first iteration, regardless of the control expression. So as we see here in this expression, cur is basically just getting the rightmost digit of x. So in this case, when we mod that huge number by 10, it just becomes 3. And then next is doing something very similar, where it divides by 10 and then mods 10. So it basically gets the next highest digit. So in this case, it would be an 8. So then we go into this next control expression where we do y plus equals all of this jumble. This, we want to put some parentheses around that so we can kind of see it maybe a little bit better. Might help to see how it works. So then we do cur mod 2, which is just 1, so that stays true for the and statement. And then we do next plus plus mod 2. But we don't add 1 yet to next because that happens after the fact. And so 8 mod 2 is 0, which is false. But then we take the not of it, so that becomes a 1. So we have 2 1s in this expression. So 1 and 1 is 1. So we do y plus equals 1. And then we divide by 10 for x. And so we'll do this next loop in a different color. So when we divide by 10, we basically just pop off that last digit. And then we repeat all of this again. So cur, as we remember, just gets the rightmost digit. Next gets the second rightmost digit, or the tens digit rather. The tens digit. And then the y, we do cur mod 2. 8 mod 2 is 0. You know what we forgot to do? We forgot to increment next after that expression. So that should be a 9 because of this increment right there that we went to. And then now it becomes 8, right? Or not 8, sorry. 7, because that's this value right here. All right, getting back to it. So we do cur mod 2. And so cur is a value of 8. So 8 mod 2 is 0. So this becomes 0. And then this expression just short circuits because nothing ANDed with 0 can be a 1. So C just basically says, oh, this expression is done, so we're not going to do anything. So therefore, next never actually gets incremented, which may or may not be a little bit confusing. So then so we add just a value of 0 to y, so this just becomes a 1. And then x mod 10 is, or not mod 10, sorry, it is divide by 10. We get 16627, so we just pop off that last digit. And then we check, does cur equal next? 8 does not equal 7. So we continue on to another loop. So cur x mod 10, that's just 7. X divided by 10 mod 10, that is a 2. And then we go into our y expression here. So we do cur mod 2. 7 mod 2 is 1, so that's true. So we go on to the next expression. And so we do next plus plus mod 2. So 2 mod 2 is 0. Then we take the not of that. So 0 knotted is a 1. So we have 2 1s. So we're going to increment y by 1 up to 2. And you have to remember, next gets incremented up to 3, right? Because we have this next plus plus here. And then we do x divided by 10 to get a value of 1662 for x. And then we continue along this process. Cur 1662 mod 10 is just a 2, and then next becomes a 6 because it's the tens digit of it. And then we do cur mod 2. 2 mod 2 is 0, so this expression short circuits again, so we just add a value of 0 to next. So next just stays at 6. And then we we divide x by 1662, or 1662 by 10 yet again, so then we get 1666. And, well, I guess, yeah, we incremented that before. And then we go back up to the top. Cur mod 10 is a 6. And then next is also 6. So then we do y. So we do cur mod 2 here. 6 mod 2 is 0. So this short circuits again, so the next plus plus never happens. And then we do x divided by 10, and we get 16. And then we check our expression again. We do cur, does cur equal next? And in this case, it actually does. 6 equals 6. So that means we break out of our loop, and we print out some of our values. So we print out x and we print out y. So x is 16, as we showed, and y is 2. And that is B, which is the correct answer. So that one's kind of a lot. It's a lot to keep track of. So just make sure you're diligent and kind of track all your code throughout the entire expressions. Okay, number 12. It's very similar to the previous question, but this time on line 12, or line 14 rather, they decide they want to put an or there instead of an and. So what this effect is it kind of changes how the short circuit's going to work. So we're going to end up with something that's an answer that's a little bit different. So we can see that should we track our code here. So we start with x is 1662783 and y is 0. So then we do cur x mod 10. So this x value modded with 10 is just a 3. And then our next value, x divided by 10 mod 10, basically just gets the tens digit. So that's an 8. That's just an 8 there. So then we go on to our y plus equals expression. So we do cur mod 2, which is 3 mod 2, which is 1. So this is a 1. And since this is an OR, we know that anything ORed with 1 is always 1. So C is like, oh, we're just not going to do the second expression. So we ignore it and short circuit it. So next never gets incremented. And we add 1 to y. And then we divide x by 10 to get 1662778. And then we check, does cur equal next? It does not. 3 does not equal 8. So then we continue along. So then cur, we do x mod 10 again to give us an 8. Then the tens digit is a 7. And then we do y plus equals. So then cur mod with 2. 8 mod 2 is a 0. So this becomes 0. So then we have to go to the second part of the OR statement, since it's not true yet. And we do next plus plus mod 2. So we do 7 mod 2. And 7 mod 2 is 1. But then we take the naught of that, so it becomes 0. So then we increment y by 0, so it becomes 1. And then we also increment next, now that that expression's over. So we increment it up to 8. And then we divide x by 10 to get 16627. And then we check our control expression. Cur does not equal next, but in this case, cur does equal next. So it's done. So then we check at the very end, we print out x. And so x is going to be 16627. And y is going to have a value of 1, which is C. Okay, number 13. This one's a bit of a doozy, because this one, if we look here in this calc expression, we see we use calc within it. So that means that we are looking at a very lovely form of recursion here. And keeping track of recursion can kind of get a little bit difficult. So hopefully I kind of outline a method here that might help you just a little bit. So our first call to calc, we do calc 5 right here. So then what we'll do is we'll keep track of some of the local variables throughout it. So we have level and mid. Those are the main two. So level is just whatever we pass in, basically. So level is 5. And mid is going to be 5 divided by 2, integer division, so we round that down. So mid's going to be 2. So then we go here, and we see is n less than 2, and n is 5. So it is not less than 2. Otherwise, we go down into this expression down here. So in this case, what we're going to be doing is we're going to be doing 5 times calc at 4 divided by 5 minus 2, which is 3, right? So if we write that back up here, it'll be 5 times some value that ends up being calc 4, and then we divide it by 3. And so what happens here, is that we call calc 4, right? That's what we said right here. And so this, whatever gets returned is going to go back up into here. This is kind of how the recursion works. So we have to go down to all the recursive calls, and then a value will get propagated back up through it. And so we call calc4 now. So then what is calc4? So what we're going to do is we're going to keep track of the variables in it. So level is just n, which is 4, and mid is 4 divided by 2, which is, of course, just 2. And so n is not less than 2, and so we go back down into this else statement. And so this else statement means that n is going to have a value of n, which is n times calc of 3, so some value that's yet to be discovered, and then n minus mid, which in this case is just going to be 2. So then here we call calc 3, and that'll get returned back up into this part of it. And so in calc 3 we have level and we have mid. So level is 3, then mid is 3 divided by 2, and your division makes it a 1. And so that 3 is not less than 2 yet, so we have to go back into this else statement here, which gives us, so then we end up with 3 times calc at 2, and then we divide it by 3 minus 1, which is 2 again. So then, like I mentioned, we are making a call to calc 2, and then that'll get propagated back up into there. And in calc 2, our level is 2, and our mid is 2 divided by 2, which is just 1. So is 2 less than 2? Nope, not quite. So then we go back into the else statement yet again, and we do 2 times calc of 1 in this case, and then we divide it by 2 minus 1, which is just 1. And then, like I mentioned, we are going to call calc 1. That'll propagate back up into here. So then our level in this case is 1, and our mid is 1 divided by 2, which is just going to be 0. But that doesn't really matter for us, because as we see here, finally, we reach our final expression, which will allow us to propagate back up through. We get n is less than 2, because 1 is less than 2. So n becomes 1. So n equals 1 in calc 1. So then when we ignore this else statement on this iteration, and we go down into this printf. So then what's going to get printed by this expression here is 1, 1. So we'll keep track of this off to the side. So we'll keep an order of what gets printed first. So 1, 1 is the first thing that gets printed. So that means that the correct answer for 13 is A. But we're going to continue through because question 14 requires the last thing printed. So we're going to track this back up through so you can kind of see how it's working exactly. So like I mentioned, we said that n here is equal to 1, and then that gets returned. So n gets returned down here. So that gets returned back up into the previous statement. So here we have a 1, so then that becomes 2 times 1 divided by 1, which is of course just equal to 2. And then like I mentioned, we print level n. So level in this case is 2, and n is also 2. So now a 2 gets printed, and then 2 is n, so that gets propagated up into here. So then we do 3 times 2, which is 6, divided by 2 equals 3. So that's what n is equal to that. So then we print level, which is 3, and then we also print n, which is also 3. And then we return n is 3, so we return it up here. So then n equals 4 times 3 divided by 2, which is 6. So then we print the level for that one. We get a 4. And then we print n, which is 6. And we propagate that 6 back up one more time, and we do n equals 5 times 6 divided by 3, which is going to be 10. 30 divided by 3, 10. And so then we'll have one final print statement of 5, 10. So then if we go to question 14 here, as we just discussed, that means that our final output of this one is going to be 5, 10. So if you're just joining us with question 14, just go back in time a little bit and see how we calculated question number 13 here as we discussed the entire way of how to do that. Okay, so we have one more question 15 here, about how exactly the recursion works. So if you remember me talking, if you saw the previous questions, this right here, this is going to be the thing that basically stops our recursion, because when we reach this, we never run this code here, which contains the recursive call. So this is basically our base case, which stops our recursion. So if we see here, this means that a recursion stops when n is less than 2. And here, every other time, which in this case is just n is greater than 2, means that the recursion continues when n is greater than or equal to 2. So like I mentioned here, this is a base case. The n is less than 2. That means when the recursive stops. And then the recursive case is when our recursion continues, which happens right here with this recursive call. So the base case, n divided by 2, right there. And then recursive case, n greater than or equal to 2, like we just mentioned. So that means B is going to be our correct answer for this question. All right, question number 16. Which of the following statements regarding solutions to repetition problems is true? First one says recursion should be reserved for processes in which there is a known upper limit to how many steps need to be taken. So this statement is in fact true, true actually, because we don't want to use recursion if we have a problem length that is unknown, because if the problem length gets too long and we have too many recursive calls, then we could run out of space on the stack, which would result in a stack overflow, which would not be desired as it would not work properly. And then let's just check the other answers, make sure they're false. So B, iterative solutions are always better than recursive ones. This is false. Iterative solutions are usually better than recursive ones, but that does not necessarily mean that they're always better than recursive solutions. And then C, an iterative solution is one that is implemented using a function that calls itself, and that's false because the situation is describing where a function calls itself. That's recursion. An iterative solution is more just using loops, like a for or a while loop. That is an iterative solution. So in that case, question 16 is A, as the other two are false. All right, question 17. Which of the following expressions would not be suitable as a third expression of a for loop that increments its loop control variable I by 1 after each iteration? So just to kind of clarify what exactly they're talking about, if we have a for loop here and we have the variable I, which gets declared, then we'd set I equal to 0, for example, and we'd say I is less than, say there's some constant defined called size. So what it's referring to is this last part of this is the for loop expression here, where we say the initial value of the loop control variable, and then we say where it's going to go to, and then the last part is where we increment it. So the possible increments are I plus plus, and this is the most common one used. So we know that that is in fact valid. So we know that this is not the correct answer. And then the next one, plus plus I. And this is effectively the same as I plus plus in the sense of a for loop, because the increment happens at the very end of the for loop. So whether you do I plus plus or plus plus I has no effect on how the for loop behaves. So this one also works. And then let's also check C. C is I plus 1. And you may think that that could work because you're adding 1 to I, but we're never actually storing this value back into I anywhere. So I never actually gets updated. So it actually end up in an infinite loop. So this number C here would be not suitable as a third expression of the for loop. Instead, what it needs to be, if it was going to be I plus 1, it'd have to be I equals I plus 1 in order to be correct. All right, question 18, a little code segment here. What is output generated by the program? And it looks like we have a print after a for loop here. So let's go through this. So we see up here that we have a size of 6. So let's check this array here, see if it actually is a size of 6. So we count, we get 1, 2, 3, 4, 5, and we notice that is not 6. So what happens in this case is whatever elements were not initialized will actually be initialized to 0 after we do this. So this means that we would have 10, 5, 1, 4, 2, 0 as our actual array. So let's go down, and so let's look at what we're printing first of all. We're printing I, and I is declared up here, and then the only thing that happens to I is that we use it in this for loop up here. So we could pretty quickly figure out what I does without going through test elements. If we see that I is first equal to 1, and then so we're going up to I is less than 6, so then we're pretty much just going to go all the way up, so 5, and then we're going to increment it once more to 6, and then this is when it breaks breaks out of this loop because 6 is not less than 6. So then it breaks out of the loop and goes into the print statement, and that's where we will print a value of I is 6, which is C. So like we mentioned in question 18, here for question 19, this size here is 6, but we only actually declare 5 numbers in the initialization. So whenever we don't declare all of the numbers, whatever ones don't get declared are actually declared to 0 initially. So that's what our array is actually going to look like. So then we have these two variables, y and I, and so y is going to start at 0, and then if we go down into our for loop here, I is going to start at 1. So then we go into test elements at I, and then so we're going to pass in a 1, and then we're going to pass in x at I minus 1, which is just going to be x at 0, which is the first element in the x array, which is just 10. And then we're also going to pass xi, so we're going to pass the one next to it, which is just 5. So then we go into test elements here, and we have this kind of gross looking expression. This is a ternary operator, and it's basically a bunch of ifs. It's basically an if statement in one line, but here they compound them, so it's kind of hard to see how it works exactly. So let's draw some parentheses. So there's a parenthesis around here and around here, as this is the first true statement of the outside ternary. So if this is true, or if this is not 0, then this expression here will be entered into. Otherwise, if this is false, then we go over to the false expression. So then on the inside of here, we have another true expression. If this is true, then we return a 2. Otherwise, we return a 1. So to make this our life a little bit easier, we can convert this into an if-else statements. So we know that this is going to be if, and then the first one is v plus plus mod k. And then if that is true, then what we're going to do is we will have another if, which is this inside one here. It'll be if plus plus w mod k. And then if that is true, then that's where we return a 2. Otherwise, if that's not true, then we get to this case, then we return a 1. And then we have the else statement for the big outside expression here. So if this is false, then we go all the way over to the 0 here. Otherwise, we're going to just return a 0. So this kind of breaks it down, makes it a little bit easier to read other than those ternary expressions. So one thing to note here is we're not actually using the values of v, k, and w after we return it all. So anything that's like a postfix, so anything like x or k plus plus or x, or I guess x isn't in here, but k plus plus, w plus plus, etc. Those aren't going to be really doing anything because we never use the values after. Something like plus plus k will have an effect because that'll happen before we do this expression. So with that logic, we can change this v plus plus to just v because we know that the v plus plus is doing nothing, just as a way to simplify it. But then we also have this plus plus y right here, or sorry, plus plus w, but that does actually do something because it'll increment w before we do the expression. So going back to the values that we passed in, we first passed in this 1, 10, and a 5. So if we go through it here, we're going to do 10 mod, so let's bring them down so we can keep track of them better. 1, 10, and 5. So we'll do v mod k, which is going to be 10 mod 1, and 10 mod 1 is just 0, which is false. So then we're going to return a 0 for the first time. So we'll increment y by 0. Then we're going to increment I on the next iteration of this for loop here because we have I plus plus. So I is going to increment to 2. 2 is still less than size, which size is 6. So we'll go back into this expression. So now we'll call test elements again with a 2, and then x at 2 minus 1, that's going to be x at 1, which is 5. And then x at I, so x at 2 is going to be 1 here. So then we pass a 2, 5, and a 1 into this. So then we do 5 mod 2, which is just going to be 1, because it's 4 with remainder 1. So that is true. So then we go down into this if statement here. So then we do plus plus w. So this is going to be 2 mod k, which is k is 2, and 2 mod 2, that's going to be 0. So then we go into this else statement and we return a 1 back up here. So that means we end up adding 1 to y. And then we increment I again, and we check is 3 less than 6, it is, so we continue through. So now I is 3, x at 3 minus 1, x at 2, well, that's just going to be 1, and then x at 3 is going to be 4. So then we'll come back down here, pass in 3, 1, and a 4, and then, so we'll do 1 mod 4, or sorry, 1 mod 3 rather, and that is going to be a value of 1, which is true. So then we go down into this expression, and we do plus plus w, which is going to be 5, modded with k, which is 3, which will give us a remainder of 2, which is true. So then we'll return 2 back up here. So we'll increment y up to 3, and then we'll increment I again in the for loop to 4. That 4 is still less than 6, so we continue through. So then we do 4, and then we do x at 4 minus 1, so x at 3, which is 4, and then x at 4 is going to be 2. Sorry. And then so we'll pass these down here, 4, 4, 2. Get rid of all this from the previous question. And then we'll do v mod k, which is just going to be 4 mod 4. And this equals 0, so that's false. So we're going to return a 0 back up to main. So we're going to increment y by 0, so we'll just get 3. Then we'll increment I in the for loop up to 5. 5 is still less than 6, so we'll continue through. So then we'll pass in 5 here, and then we'll do x at 4. So 0, 1, 2, 3, 4, so that's 2. And then x at 5 is 0, 1, 2, 3, 4, 5, which is 0, so that's our last element. So then we'll get rid of all this stuff down here, and then we'll pass in the 5, 2, 0. So we'll do 2 mod k, which is 5, which is going to equal just 2. So that makes that true. So we'll go down into here, increment w by 1, so we'll get 1 mod 5, which is going to equal 1. And then so that is true, so that means we're going to return a 2 back up to here. So that's a 5. Then we'll increment I by 1 again at the end of the for loop. And then we'll check, is 6 less than 6? It is not. So then we break out of our for loop, and then the next thing we do is print y. So we'll print y is 5, so we get A, which is the correct answer. Alright, 20. Looking at the same code here, which of the following statements best describes the behavior of the for loop on lines 12 through 15, which is right here? What describes it the best? So the A says there are 5 evaluations of the loop control, but there's only 4 iterations. B, 6 evaluations, but 5 iterations, and then C, 7 evaluations, but 6 iterations. So if you remember correctly, our I values, it starts at 1, and then we go to 2, 3, 4, 5, and then we increment once more to get 6 to check, does that leave, or does that exceed the size, which it does. So if you see here, that's exactly what this is, 1, 2, 3, 4, 5, 6. So we evaluate, these are all evaluations of the loop control expression. So we evaluate it 6 times, but we only actually ever iterate 5 times, because we only iterate on these ones. Because on this last one, on 6 here, that exceeds 6, or it exceeds the control expression that we're looking at, because 6 is not less than 6. So that means that that one doesn't actually count as an iteration. So therefore we only have 5 iterations here, but we have a total of 6 evaluations of the loop control expression. So that gives us an answer of B. Alright, question 21. Which of the following statements best describes what occurs when accessing an index beyond the bounds of an array? So this basically is talking about if we have some array defined as a size of 5 here, say we initialize this or whatnot to 1, 2, 3, 4, 5, like so. And then what if we do array at 6 or something like this? What's going to happen? This is what this is asking. So the first one says the array will automatically expand and the new elements of the array will be initialized to 0. That is not true, as there's no sense of automatic expansion of arrays in C. Any expansion of an array you have to do by yourself, so that's not true. The program will always fail to compile. This is actually not true. It doesn't necessarily check if you're exceeding the bounds of your array, and this can be problematic when you're trying to debug things, because it won't tell you explicitly that you are out of bounds of your array, like some programming languages like Python will. So then you have unexpected behavior that happens, not realizing what's causing it. So this is false. And then the program will always crash or end prematurely. This is actually also false. because sometimes it won't destroy anything. Sometimes you can have it'll like mess everything up because you can have like a segmentation fault or something. But oftentimes it'll still work. It'll just behave really oddly because you're accessing out of bounds memory locations, and there's actually just numbers at those memory locations. So it'll just plug in whatever number that is, and that's usually some very large or very small number. So it'll end up working, but the results will be very weird. So since all of these are false, the correct answer is D, none of the above. All right, 22. Which of the following expressions should be the condition of the if statement on line 31 in the function? So if we see here, unlike a lot of the other ones, we only have a function here. We have no main. So if you go to compile and run this code, you're going to get a lot of errors because there's no main function. But if you want to add a main function and make some calls to it, you totally can. So what this function is, or what this question is referring to, is this statement right here, question 22. So if we look, so we have some big switch up here for the month, basically figuring out the number of days in the month. But then the part of the code that's pertinent to us is this part right here. And if we see here, this looks like a pretty standard input validation type of problem that you'd see in your like lecture notes, or perhaps when you're doing a homework or a lab. Because we have a do while loop, and we print out entering the month, day of the month, and then we scan in that value, and then it's wanting us to check here if the day is between 1 and %d, and in this case %d is just max days. So what it's wanting us to check is the day, is it between these two values of 1 and max days. So if you were in math class, you'd kind of write it like this, where 1 less than day, or day is greater than 1, and then day is also less than max days. So that's what we need to basically fill out for question 22 here. And so this first part, it'll just be day is less than 1, right? Because that's what we say right here. And then the other part is going to be day is less than max days. So then the part to figure out is what do we put between it? Do we put an and, or do we put an or? So if you think about it, if the value is 0, 0 is less than 1, so it'll be outside the bounds. But 0, I suppose 0 is also less than max days. Or, oh, sorry, this is not less than, this should be greater than max days. Yeah, like so, because we need to check if it's outside of the bounds. Because if it's less than max days, then it's actually inside the bounds. So if we give this a value of 0, 0 is less than 1 is true, but 0 is not greater than max days. So basically, only one of these is ever going to be true on the case where day is outside of this range. So these two expressions, just to clarify more, are checking if it's outside of the range. Here, we're just checking, this is the range we need to check, but we need to check, did it get outside of this range? So this will result in, we just need two ors here, because one of these is going to be true. It's impossible for them both to be true at the same time. So this gives us B as our answer for question number 22. So now to 23. All right, so question 23, very similar. It's just asking us to check right here, down here, what should be the expression down here. And if you remember from your lecture notes, probably, anytime we have an input validation here, they say that this expression here and this expression should be exactly the same. So by that logic, our answer again is just B, as that's what it was before. Because basically, here we're checking, is there an error or not? And then we print the error. And so we only want to loop this when that error exists, so we need to use the same logic, because we know that's when the error is present. So these will always have the same exact logic. If you're confused about that, I'd look at your lecture notes, as I remember they talked about that in detail, at least when I took the course. All right, question 24. What is the last line of output in the program? Okay, so let's start up here in main. So we have x, which is initially 25, and then we have a do while loop. So we just go right into the loop, and then we check is 25 prime. So before you just trust that this is actually checking if a number is prime or not, we can do a quick little check to see how this is working exactly. So this check right here checks if it's divisible by 2, if x mod 2 is divisible by 2. Because if it is, then we set j equal to 0, and then this never starts, so then we just return 0, so it's not prime. So this effectively just checks if it's divisible by 2. And then if it isn't divisible by 2, then we take the square root of it, and that gives us an upper range on where to find if it's a prime number or not. If you do some research about like prime numbers and such, you'll find that you don't really need to check any of the numbers above the square root of the number, as then you're just going to be double checking values. Because like if we have 25 here, and then we do 5 times 5, the next numbers, I guess this is not a great example. Let's say we do 36. So if we do 6 times 6, then we know that's obviously the square root of 36 is 6. And then if we go up to another one, so before this could be 3 times 12, and then we increment all the way up to 6. But then we're just going to be decrementing back down, so we'll get 12 times 3. So basically just going to have a bunch of repeats. So we only need to go up to the square root of x. So that is valid. And then this just starts from 3, goes up to the square root of it, and then increments by 2 each time. And that way you don't have to increment by 1. And then this expression here just checks, is it divisible by I? And if it is, then j is equal to I, which is, or j is equal to j, which is just going to be some number greater than 0, otherwise it's equal to 0. So in essence, this does correctly check if the number is prime or not. So we can use that knowledge and not have to run it through all this code every single time. So if we come back up here, is 25 prime? No, it's not, because 25 divided by 5 is 5. So we don't print out anything. So then we go down into this loop control. So we do x minus minus 10, or mod 10. So this is going to be 25 mod 10, which is going to be equal to 5, does not equal to 1, which is true. So we'll continue through this while statement, and then we'll decrement x by 1. So then we check is 24 prime, it's not, 6 times 4. And then, so we'll go back down into this expression, and then we get 24 mod 10 does not equal 1. 24 mod 10 is 4, does not equal 1, which is true, so we'll continue through. Decrement this by 1 again. 23, well, that actually is prime. So 23 is prime, so that means that this expression here will get activated, so then we're going to print out x at 23, and that is in fact our first line of output. So the correct answer for this question is C. Alright, 25. So now it's asking us what the last line of output is. So if we continue our work from question 24 here, we had 25, then 24, and then 23, and that's when we printed 23 right here. So we'll continue through until this entire thing ends, so basically until this statement gets executed here. And as we talked about before, this function actually does check if it's prime or not, so we can check the validity of, we don't need to run the number through there. So 23, we need to bring it down into this check. So we'll do 23 mod 10 does not equal 1, so 3 does not equal 1, so then we continue and decrement x by 1. So that gives us 22, and then we say is 22 prime? It is not prime, so then we don't print anything there. And then we do 22 mod 10, which is 2, which does not equal 1. So we go through the loop again and decrement down to 21. 21 is also not prime, so then we do 21 mod 10, which is 1. So 1 equals 1. So then this while loop is going to be broken out of. But then we also need to remember we have to decrement x by 1 again after this expression. So we have to make sure we decrement it, and then we finally get to this print statement where we print x is 20, which is the correct answer. Alright, which of the following statements regarding nested repetition is false? Alright, A, 2 or more repetition processes are considered nested only if they appear in the same user-defined function. So we're looking for the false one here, and this is false, actually, so that's false. This is because we could have a loop in main, and then we could have a loop inside a user-defined function that gets called in the loop in main, and that's technically nested. So for clarification, if we write that out really quick, so if we have main here, and then we have some for loop with all the loop control expression in there, and then we have a function called foo that we call in here, and then say foo is defined down here, and inside of foo is another for loop like this, and then we do whatever we want to do with the for loop, and then we return back up to main. So basically this is a loop inside of a loop, because inside the for loop here we call foo, and foo has a for loop inside of it, so we have a nested for loop. So this is technically nested even though they're not in the same user-defined function, which makes A false. And then we'll check the validity of B and C just to check. So B states that separating each repetition process into its own function can make solving nested repetition processes easier. And this is true, just because, like in our example here, this is where we separate it into different functions, as sometimes the outside and the inside loops are doing something completely different. So putting them into different functions can make it a little bit easier to understand why it's working and how it's working properly. And then C, testing the solution of the inner repetition process first can make it easier then to work on the outer repetition process. This is also true. Usually you just want to work inside out with loops, as you want to start with the one that's getting incremented the most, and then you can see the bigger loop on how that one's incrementing through the list as a whole. It's much easier to work inside out than outside in with loops. And that's more something that you kind of, I don't know, that's just more something you have to know as opposed to a ton of intuition. All right, question 27 here. What is the output generated by the program? We have a lot of variables, it looks like, on this one. So we have an A, a B, a C, and an X, and they're all starting at 0. So this looks like it's going to be testing us on our short circuit knowledge and our knowledge of order of operations, probably. So on this one, there's no parentheses drawn, and so as you see here, when I say that there's some warning or whatever when you run this code on boiler exams, that's because they didn't include any parentheses around these, but the code is still valid. I don't think it'll throw a warning on Vocarium or wherever you compile it for the course, so it's still valid. So if we need to draw our parentheses, so remember and comes before or. So if we draw our parentheses for all of these, then we get something that looks kind of like that. And then so we're going to do A plus plus, so 0, ANDed with plus plus B, which is going to be 1, because we increment it beforehand. So 0 and 1. Hold the phone. We do not. Okay, so since this is 0 here, and we're in an AND statement, nothing ANDed with 0 can be true, so this is going to short circuit, and actually, this is never going to happen. So we're never going to do plus plus B, and then this right here is false, or it's 0. And then so since we have an OR, we need to check the other expression to see if that one's true. So we do C minus minus, and C is 0, so that is also false. So we add 0 to X here, and then we subtract 1 from C, and then we add 1 to A. But we never increment B because that never actually got evaluated. Oh, looks like we erased something there. Okay, so then we do A plus plus again. So that is 1 right here. And so 1 is true, and since we have an OR statement, this entire other expression just never gets happen. It gets short-circuited because anything ORed with 1 is always true. So C just says, oh, the rest of this doesn't need to be executed. So then we just have a 1 here. So then we increment X by 1 up to 1. And then we increment A by 1 as well at the end. But we don't increment B or C because those never got executed. Okay, and then we do 2, which is true, so we continue into the next part of the AND. 2 and plus plus B, which is 1, because we do it beforehand. So then 2 and 1 is true, but then we take the not of it, so this all becomes 0 over here. So then we do need to use this OR because we need to see, could this be true still, even though the left side's false. So then we do C minus minus, and, oh, wait, oh, my parentheses messed me up here, sorry. Okay, because this OR applies, or this not applies to the entire outside one, not these inside parentheses that I was using. All right, so let's go back to it. So we have a 2 here, and then plus plus B, which we said was 1. So we do 2 and 1, which is true. So then we don't actually do this part of it, because this is an OR statement, and we know the left side is true, so no matter what the right side is, this will always just be true. So C minus minus never actually gets incremented. And then we take the not of 1, which is going to be 0, so we just add 0 to X. And then we also have to remember we have to increment A at the end, so we get 3. So then when we finally print this out, we get A is 3, B is 1, C is -1. And so if we look at our correct answers here, that is in fact C, which is the right answer. Okay, next question here, 28. Which pair of logical expressions in the program above are complements of one another? And so complements, if you're unaware, are logical expressions which are exact opposite. So what this means is anytime, say we have two expressions, one is this green one and one is this blue one. Anytime the green one is true, the blue one is false. And anytime the green one is false, the blue one is true. So they're exact opposites of each other. They give you the exact opposite logical result. So if we look through our expressions here, we'll find that B is the logical expression that are complements. And it's actually relatively straightforward here because we see We have all of this here. And then we have this exact same code on the inside of this set of parentheses here. So that's the exact same. A plus plus ANDed with plus plus B ORed with C minus minus. That's the exact same. And then we just take the not of it. And so this not is effectively behaving as the logical complement, as whatever the answer of the inside is, we take the opposite of it. So these two are always going to have opposite results, because X and X exclamation here, X not, those are always going to be the exact opposite of each other. So the same holds true for B here, which makes B our correct answer. And then so if we look at our other answers here, we have A plus plus ANDed with plus plus B ORed with C versus A plus plus ORed with plus plus B ANDed with C minus minus. These aren't logical complements because the only thing we changed was just the ands and the ors, and that's usually not enough for two expressions to be complements of each other. And then C, it looks somewhat similar to what we did for B, but they switched the order of the ands and the ors, but that changes the behavior of it, so it doesn't act as a logical complement. So if you're unsure if it's a logical complement or not, what I'd recommend is for all the values inside of it, so for A, B, and C, you could check all of the possibilities, so like 1, so this would give us all of our possibilities here. 1, 0, 1, 0, 1, 0, 1, 0. So there's 8 different possibilities, so you could check all 8 possibilities and see if they're the opposite for the logical expressions. So if you want to check, go ahead and do it that way. All right, which of the following statements regarding the usage of Srand and Rand functions is false? Okay, so A states that the parameters to the Rand function limits the range of the possible random numbers generated. This actually is false, because Rand has no parameters. Because when you call Rand, you just call it like this. There's no parameter that gets passed into it, because if you want to do a range, you have to use modulus to actually put it inside of a range. So that is false. So we'll check B and C as well, in case those tripped you up. So B says the parameter to the Srand function causes the program to generate a sequence of random numbers that is consistent between multiple executions of the programs. So that is true. If you remember what Srand does, it sets, I guess we need to pass some value to it. It sets the seed of our random number generation. And so what the seed of our random number generation is, that is basically the starting point of our random generation. So the way random generation works in most languages is we have some starting point, and then we perform a bunch of math operations on it that effectively make the number random. So if we give it the same starting value each time, the same math operations are going to be performed, so we're going to result in the same random numbers. So that's why you use seed values in your labs and homeworks, because then it allows for the same executions to happen over and over, and it allows for them to check that they get the same results as you. So basically, this is true because it creates consistent random numbers between the executions of the program. And then C, the Rand function returns an integer, whereas Srand is a void function. So this is true. Srand is a void. We don't need anything to be returned from it. But then Rand returns the random integer that we generated. So that makes that true. So question 30, which of the following statements regarding looping constructs is false? A states that code that is duplicated inside and outside of a loop may indicate that the wrong looping construct is being used. So this is true. In fact, usually if you have duplication of code, that usually means you're not doing something as efficient as you could be. The best example of this specific one is when you're doing input validation. If you were to use a while loop instead of a do while loop, then you'd have some duplicated code, because you'd have to print out the message you want to show the user, and then you'd have to scan in the value here, and then you'd have to enter the loop again, and then you'd have to duplicate this code back into here every time that there's an error. Whereas if you just did a do while loop here, you'd only have to do this one. You'd only have this printf and this scanf once inside of it, because this basically will get evaluated before the while loop ever gets evaluated. So this first part will always be evaluated, and then it'll loop through. So in this instance, we're using the wrong looping construct, because we should be using a do while loop, because then there's not as much code duplication. And then B, in a while loop, the control expression is evaluated n+1 times for n iterations. So we've seen lots of problems on this exam so far that kind of talk about the loop control expressions. So this is true because we always have one extra evaluation, because this is the case that'll fail the loop control evaluation, and so we won't iterate on it. So we're always going to have one more evaluation than we will have iteration. So that's something you can kind of just remember. And then C, the while loop will iterate a minimum of 1 time, and the do while loop will iterate a minimum of 0 times. So So this is false, so this is our correct answer because they flipped them. So do while loop is the one where it'll iterate a minimum of one time, because this will iterate right here, and then we'll evaluate our expression. Whereas in a while loop, we evaluate the expression and then we iterate. So this could be false right away, so we could iterate it 0 times. So that makes C false, and which makes it our correct answer. All right, 31. Which of the following statements regarding floating point numbers is true? A, the C language prohibits the use of the operators equals, greater than equal to, less than equal to, not equal to with floating point operands. This is false. This is perfectly legal. We can have 1.0 less than or equal to 2.0, something like that. That is legal. You can use logical operators with floating numbers. B, it is better to check that the difference between two floating point numbers is within a certain range rather than testing for exact equality. So this is kind of a weird one, but this is actually true. Because rounding errors and precision errors when you're dealing with floats or doubles can make our calculated values slightly wrong, actually. So say we're taking like the cosine of some number and we expect it to be exactly 1.0, but sometimes it might be like 1.000001. So what's better is to check between a range of, I don't know, like maybe 0.99 and 1.01. Check between that, see if the number falls between that range, to see if they're equal to. So that's a pretty good practice to have with most languages. Some languages even have that built into it, as that's a better way to check for equality. Okay, and then C, floating point values can use case labels for a switch statement. Floating point values used as case labels for a switch statement will be converted into integers. That's false. It'll just use the floating point values. It won't try and convert them into integers, because as we mentioned before, the equals perfectly legal to use as floating points, so the same holds true for C here. All right, 32. What is the output generated by our program? So this one's a bit of a long one, so we'll just go ahead and jump into it. So the only thing that happens in main here is we just make a call to this function find digit and pass the value into it. So we have our value num inside of here, and then we also have digit, and we also have found, which are the ones we are interested in keeping track of. So number is initially 1, 5, 9, 7, 4, 6, 0. Digit is not initialized, and found is equal to 0. So then we do while num is greater than 0. We do digit equals num mod 10, which just gives us the last digit in num, which just gives us a 0. And then we check, is digit greater than found? So is 0 greater than 0? That is not true. So then we don't do anything. So then we just divide num by 10, integer division wise. So we just get rid of that last digit effectively. Let's make this a different color, 1, 5, 9, 7, 4, 6. So then we iterate through this again. We do digit equals num mod 10, so then we get digit is a 6, and then we see that 6 is greater than 0 here, right? So then we set found equal to the digit, so that's 6, and then we just divide again by 10. So if we take a step back and kind of see what this loop is doing, basically what it's doing is it's putting this number closer and closer to 0, so we just take off each digit at a time. So eventually this will be a 4, then a 7, then a 9, then a 5, then a 1, and then we compare it with this found number. We see if it's greater than it. So basically what this is doing is it's just finding what is the maximum digit within this big number here. And we can just visually look and see that the biggest digit is going to be 9. So that means found is just going to be 9. So we can kind of just quickly do it that way instead of having to trace through all of this code, which makes our life a little bit easier. So then if we go down to the next loop here, we'll see that digit is equal to 0 initially. And then we have some for loop where we go from 0 to less than or equal to 3. So that means I is going to be 0, 1, 2, 3, and then one last 4 to check the loop control expression. So then in each one of these loops here, we can kind of rewrite how this looks. So we're going to do plus equals 10 to the I, because pow, I, and then that'll just be some integer value. And then we multiply it times found, which we know is going to be 9 because that's not changing. And then we divide that by 2 to the I, and then we mod by 2. So if we just go through this, so this is digit plus equals this. The first time we do this, I is going to be equal to 0, right? So when I is equal to 0, that means that we're doing 10 to the 0, which is 1, so we'll do 9 divided by 2 to the 0. 2 to the 0 is just 1, so this will just end up being 9 mod 2, which is equal to 1. So that means digit is going to have 1 added to it. And then on the next one, I is going to be equal to 1, because we increment it by 1, and that is still less than or equal to 3. So then 10 to the 1 is 10 times 9 divided by 2 to the 1, which is 2, all modded with 2. So then we get 9 divided by 2, which is going to be 4, because we're doing integer division. And then we do 4 modulus 2, which is just going to be 0. So, and then 10 times 0 is 0. So this will just be 0, so we're adding 0 to it. So add 0, so we still just have 1. And then we increment I again, so we get I equals 2. That is still less than or equal to 3. So then we do 10 squared, and then 9 divided by 2 squared, which is 4, modulus 2. So then 9 divided by 4, integer division, that is just 2. Then we do 2 mod 2, which is 0. 0 times 10 squared is 0 again. So we just add 0 once again. And then we do increment I by 1 again, we get I equals 3. So then we get 10 to the third times 9 divided by 2 cubed, which is just 8. And then we modulus that with 2. So 9 divided by 8, integer division, is just 1. 1 modulus 2 is 1 also. So we do 1 times 10 to the third, which equals 1,000. So then we have to add 1,000 to our digit, and we get 1,001. And then we increment our I. Yet again, we get I equals 4, but that is not less than or equal to 3. So we break out of our loop, and we return our digit, and then back up here in main, we print out that digit. So that digit is 1001, so our answer is B, which is a correct answer. All right, question 33. The parameter to the function call has now changed, and it's asking us what is the output generated by our program. So our new number here is 61537. And if we remember here, as we discussed in the previous question number 32, you can go back and watch that if you need. We discussed that this while loop effectively just finds the biggest digit in our number. And so the biggest digit in our number, so our found, that's just going to be 7, because 7 is bigger than all of these digits here. So then we'll go down into our next loop and look through it. So digit, we're going to start with digit equals 0. And then if we remember properly, this is 10 to the I times found, which is 7, divided by 2 to the I modulus 2. So the first iteration here, I, is equal to 0. So that means we're going to do 10 to the 0, which is just 1, of course. And then 7 divided by 2 to the 0. 2 to the 0 is 1, so we just get 7. So we do 7 mod 2. And 7 mod 2 is 1, so our digit's going to increase to 1. Then we're going to do 10 to the 1, which is 10, times 7 divided by 2 to the 1, which is just 2, modulus with 2. So 7 divided by 2, integer division is 1. So 1 modulus 2 is 1. So we do 1 times 10, which is 10. So then our digit becomes 11. Sorry, I forgot to mention we incremented that by 1 there. So now we increment by 1 again. So now I is equal to 2. So we get 10 squared times 7 divided by 4, modulus with 2. 7 divided by 4 is just 1 with integer division. 1 modulus 2 is also just 1. So we do 1 times 10 squared, which is just 100. So we add 100 to this now, so we get 1, 1, 1. And then we do I equals 3 now. We increment it, that's still less than or equal to 3. So then we get 10 cubed times 7 divided by 8, modulus 2. And 7 divided by 8 is 0, so 0 mod 2 is 0. 0 times 10 to the cube is 0. So this is all just adding 0. So we still just have 1, 1, 1. Then we increment I by 1 yet again. That gets us 4, but that's not less than or equal to 3, so we break out of the loop. Then we return 111, and then back up here in main, we print out 111, which is, in fact, our correct answer. All right, and then we have our last question here for this exam. Which of the following statements regarding multi-way else-if constructs is true? The first one states, the if condition is evaluated first, and additional else-if conditions are evaluated until all true conditions have been found. This is false. This is not how if and else-if statements work. It only executes until one true condition is found. As soon as one of the true conditions is found, then none of the other else-ifs or else gets executed. So that's false. Then B, The else is executed only when all the previously evaluated conditions are false. This is true. This is how else works. Because basically, if we have a bunch of if and then else if, so on, and then we have an else, that's else is only going to be executed if all of those are false. So that's true. And then we'll just double check C. The usage of multi-way else if is always preferred over the usage of switch. This is not necessarily true. This is false, and something's usually never always preferred, just as a word of advice. Switch is usually better with large constructs just because it doesn't take up as much time. Say you're trying to figure out what day of the month it is or what month it is, something like that. Switch can be better because it doesn't have as much code that you need for it. So that's false, which means B is our correct answer. And that means that we're at the end of this exam. So if you have any questions or comments, please leave them in the comment section below, and hopefully this was helpful.